So what is this IPv6 business, you ask? I'm sure you have seen it. I'm sure you've worked with it to some degree. And I'm sure you've seen IPv6 addresses in your systems, especially if you've had Windows 7 or later systems. You will see IPv6 addresses and IPv6 automatically enabled. Let me show you what I'm talking about. If I do an IP config over here, I notice an IPv6 address right there. Okay, right there. And this is on a Windows 8 system. And if I open up the control panel in Windows that allows me to get to protocols, notice right over here I have access to TCP/IP version 6 and go to properties and start manipulating it. And this has been around since Windows 7. So many systems, not just Windows, even in the Linux environment, IPv6 is around. So here's a basic OSI 7-layer model that starts with physical layer on the bottom and ends with application layer on top. And the first 3 layers, if you're really thinking about the IPv4 arena, TCP/IP starts at layer 3, or the network layer. It's at this layer that IP sits. Layer 3 is where IP is, and layer 4 is where TCP is. Layer 4 is where TCP sits, along with UDP. So physical communication, and of course the information is going from device to device, okay? And then you have an intermediate node, if you will, in this particular instance, a router, a switch, whatever is responsible for taking the data across from one point over to another. I suppose you could have a crossover cable that connects these two together, but then you'd have only one device. We won't go there. So 7 layers of the OSI model, and the top 3 layers, the upper layers, if you will, is really where HTTP, DHCP, DNS, all of those are sitting at the top 3 layers, right? So IPv4 has been around. You know how long IPv4 has been around? There's an interesting trivia question. When was IPv4 developed? Do you know? It was in 1981. 81. You believe that? And we are still using it. Here we are several decades later. IPv4 was defined and revised. And of course, it has been revised since that time. But the definitive initial guide, if you will, for IPv4 was created in 1981, and largely IPv4 is still used very, very heavily. Of course, it hasn't exactly gone away. Everybody still recognizes the IPv4 addressing scheme. Most organizations I work with, and perhaps you work with, are utilizing IPv4 on their desktops, on their laptops, on their servers. Most admins only understand IPv4 clearly. They're the ones that are assigning IPv4 addresses. Your devices, such as your routing devices, your storage devices, they've been around and with IPv4. I know that Cisco began supporting IPv6 in 1997 on all of their devices. So Cisco's been supporting IPv6 for quite some time. I'm not really sure how many were using IPv6 in those days, or how many people even understood or recognized what IPv6 was. People are still gaining the information and knowledge about how to work with IPv6. It's a very important piece of the equation. You do want to learn IPv6. You want to learn about what IPv6 is, how it works, and that's something that I'm going to be walking you through, and some of the differences between IPv4 and IPv6. Lots and lots of things have changed. IPv4, why is the need for IPv6? You think about that, right, for a minute. IPv6, the addresses in IPv4 are exhausted. Everybody will tell you that. Hey, the reason IPv6 came around was because the addressing scheme in IPv4 was exhausted. That's not entirely true by itself. Yes, that is true. IPv4 addresses were exhausted, are exhausted, but that's not the only reason IPv6 came around, not just to give us more addresses and more of an address space. There's a lot more going on that IPv4 simply wasn't quite ready for. If you think about it today versus 1981 when IPv4 was developed, what kind of data are we pushing through our systems today? Is it only text data or normal computer data, if you will? That's not really the case, is it? We're moving streaming video, we're moving images. Not only that, our networks are now cloud-based. We got data on mobile devices, on tablets, on devices that are just moving around all over the place. We're a very mobile society, so we didn't really have a protocol that tied well with that up until now. So here's the IP protocol suite. Here, for example, are the top 3 layers. You've got SMTP, the Simple Mail Transfer Protocol. Your messaging applications sit here. File Transfer Protocol, Hypertext Transfer Protocol for your web servers in this particular instance. Your domain name system would be sitting here, for example. Your CCNP, the Simple Network Management Protocol for the purposes of network management. Telnet would be sitting here. DHCP would be sitting here, right over here. DHCP would be sitting here, for example, in one of these things. So all of that is sitting at the top 3 layers. Okay. At the transport layer is where you have TCP and UDP, right? TCP, the Transmission Control Protocol, and User Datagram Protocol. Right? One is connection-based and one is connection-less. At the network layer, you have IP, okay? And you have IGMP, the Group Management Protocol, the Internet Control Management Protocol, Reverse Address Resolution Protocol, Address Resolution Protocol. ARP is responsible for translating IP to a MAC address, and RARP, Reverse Address Resolution Protocol, is responsible for translating a MAC address to an IP address. Using ICMP, you are able to manage its Internet Control Message Protocol. You're really able to receive and send management information. Echo requests, namely ping, operates at using ICMP requests, for example. Okay. Then you have data link and physical. Now TCP/IP doesn't sit over here. Why? Because these layers are physical in nature. And what happens is at the data link layer, you have LLC, the logical link control, that is what's connecting layer 2 to layer 3. And you have a MAC address, which is connecting layer 1 to layer 2, right? You have MAC address, which is connecting layer 1 to layer 2. So logical link control is connecting the 2 layers together, 2 and 3. So right over here, you've got, this is layer 1, this is layer 2, this is layer 3, this is layer 4, and these are layers 5 through 7. Okay, so keep that in mind. The session, presentation, and application layers, by the time your packet comes to this stage, it is very, very top-heavy, if you will. It contains a lot of intelligent information about where it's coming from and where it's going, but it is also kind of slow in nature, if you will. At the physical layer, the data is being transmitted in the form of bits and bytes. At the data link layer, the information is known as a frame. Okay, so right over here, the data would be known as a frame. And it is at the network layer that the data is known as a packet, as like a network packet, right? IP packet. And it is at the transport layer that the data is known as a segment. And it is at these upper layers that the data is just known as a message. So each layer adds its own overhead, if you will, to the actual packet that is being transmitted. Now, IP, there are a few features of IP. It works at the network layer of the OSI model. And the network layer of the OSI model is the very first layer that holds or allows for understanding logical information or logical addressing. The layers prior to this, layers 1 and 2 do not understand logical addresses. They understand, let me clean this up. Okay. They understand MAC addresses or physical addresses and physical connectivity. The TCP/IP protocol at layer 3 is unreliable, connectionless, and uses datagram, and it does what's called a best effort delivery. Well, what does that really mean? Well, that really means that when I ping something, let's say I was to ping, right, and I get a reply back. Now, the only reason I'm getting a reply back is because Google is replying back. If I ping a host, let's say I just say nohost.com, look, okay, I get a reply back, right? If I ping something that doesn't exist, like this, okay? So if I ping something that doesn't exist, I really have no way of knowing if this really doesn't exist. I have no real way of knowing if this really doesn't exist, or if this is replying to me that way, if the ping requests have been denied. And the other thing that may be more common to you as far as best effort delivery goes, it's kind of like an email. When you send an email to somebody, it's going to try to deliver the email. It does do a best effort delivery because most of the time it does get there. But you really have no way of knowing if the email reached the other side unless the recipient replies and says, or acknowledges and says, I got the email. Right? Otherwise, you have no way of knowing. Connectionless. Well, connectionless really works just like an email as well. That means that when you send an email from your desk, from your machine, the other side does not have to be ready and waiting to read your email. It doesn't work that way. You can send the email and the other end will receive it whenever they're ready to receive it. That's connectionless. Both sides do not have to be up. Okay? It's also, connectionless used to be described also as walkie-talkie. When you talk on your walkie-talkie, the two-way radios, if you will, when you're talking, the other side doesn't have to be listening. The other side doesn't have to be listening in order for you to communicate. It's, one person talks at a time. Very different than connection-based, which is like a phone call. Both sides have to be on the phone in order for the communication to take place. That's connection-based. So the popular version of IP is IPv4 right now. Okay, major functions, global addressing, the datagram lifetime, and fragmentation and reassembly. Fragmentation and reassembly makes it possible for packets to be sent in any order and they get reassembled on the other side in the correct order. Here's the IPv4 header. Okay, here you got the bit 0 all the way up to bit 31, right? Total of 32 bits. And this way we have 20 octets. Okay, this way we have 20 octets. We have options and padding. We have a destination address, a source address. We have a time to live, a TTL, associated with this particular packet that is the header that is going out. The protocol that is being utilized for the purposes of this particular IP header. There's a header checksum which confirms that the data got there in its entirety. Identification, flags, the fragment offset, the total length, type of service this is, an IHL, and a version. Okay. This is the IPv4 header by default. Right. This is what the header looks like. Okay. Now, IPv4 has some companion protocols. I told you about some of these already. For example, the address resolution protocol, which will map an IP address to a MAC address. Okay. Your network card, your NIC, has a MAC address assigned to it, right? Your network card has a MAC address assigned to it, and that MAC address is the one that needs to have an IP address assigned. You cannot have an IP address assigned to nothing. It has to be assigned to a MAC. If I do, maybe make this screen a little bit bigger so that I can show you very, very clearly. Change this font over here, make this thing a little bit bolder, and click OK. And if I do ipconfig /all, here is the physical address of my device. That's the MAC address that this IP address is assigned to. No MAC address, media access control address, that's what MAC is, no IP address. Okay? So MAC addresses are the ones that are assigned IP addresses, and ARP will map an IP address to a MAC address, just like RARP, a reverse address resolution protocol, will map a MAC address to an IP instead of an IP to a MAC. Internet Control Message Protocol does error reporting and querying, so ping is part of the ICMP request as well. The Internet Group Management Protocol, it allows you to join, leave a multicast member. Okay? Unicast routing protocols such as intra-autonomous system, intra-AS, will maintains a unicast routing table, such as routing information protocol, open shortest path first. Unicast allows you to send a message to one device. Okay? Unicast will send a message to one device, which is very different than multicast, which can send messages to multiple devices, as you might imagine. And then there is broadcast, which sends a message to all devices. The difference between unicast, multicast, and broadcast is really the amount of traffic that it creates and the type of protocols that are used to accomplish that task. All right. There are multicast routing protocols, all right, that include the DVMRP, the MOSPF, multicast open shortest path first. There's CBT, there's PIM, and you have to maintain a multicast routing table so it knows where it's going to be going to. Then there's exterior routing protocols such as border gateway protocol, and it's inter-autonomous system instead of intra. Then there's a quality of service framework, or QoS. QoS is very important. The integrated service, ISA or INSERV, and then there's differentiated services that exist as well. Quality of service would dictate how well the protocols behave or how well the data reaches the other side, what kind of error rate you have, what kind of drop rate you have. Quality of service is very important. It allows someone, a management, to dictate that 99.9% of the data or the packets that were sent from this location end up on the other side. If you don't have QoS metrics, you don't know how many problems you're having. You don't know if there's a problem with a device, a cable, a network card, a router, a switch, something in the middle, something in an ATM, something in the cloud. Where is the problem? It's really hard to see when you have, or when you really are not dealing with, when you're really not dealing with QoS. QoS reports are provided centrally, and you're able to increase or decrease your quality of service depending on the fact on how well the other end is able to withstand the problems that take place. If there are too many drops in packets of data, now think about this for a minute. When you're talking on your phone, have you ever had your voice garbled up on the other end? You know that when you talk on the phone, there is a bit of a delay from the time that you talk on the phone to the time the other end receives the messages or your conversation, what you're saying. There is a little bit of delay. And that delay occurs when the packet is traveling. If you don't believe me, talk to somebody in the next room. Pick up the phone, dial the person who's in the next room, and you'll notice that delay. You'll notice that seconds delay, if you will, that it takes for your voice or the data in this particular instance that happens to be voice to reach the other side. If your voice gets garbled up, you have to speak again because the other end didn't understand you. That would be an example of a quality of service related issue that would need to be handled. Your service provider, your telephone service provider, your mobile device provider, service provider, is constantly looking at what and how much data is being garbled up, where the pockets of problems are, and they begin working on those problems immediately, and that's how come they're able to offer a range of service that covers most of the city, state, national, or global boundaries. Okay, so quality of service. So why IPv6? Well, no kidding, we have a deficiency of IPv4 addresses. As I said, the IPv4 address space has been exhausted, if you will. So there's new types of service, such as integration of multicast, the quality of service. Security is another really big deal. Security is a really big deal, and mobility is a really big deal. I want to ask you, since IPv4 was around, for example, in 1981, what kind of security needs and mobility needs existed back in 81? Can you think about that? If you were around at that time, you can ask some other people around you that were around in 1981 and ask them what was meant by computer security back then. I can tell you, because I was around in the 80s, early 80s, and I can tell you that security associated with computers and technology ended at lock and key. If you want to protect your computers, you close them behind a door and you make sure that you're the only one that has the key. That was security. There was no real concept of somebody being able to remote into your computer. Personal computers that we see today, they're not really very personal anymore. We really didn't have someone trying to get into our machines and gaining access remotely. That was rare, as a matter of fact. It became more and more prevalent in the mid and late 80s via remote devices that allowed you to communicate over online. And really online, I'm not talking about internet. Internet did not exist the way we see today. The World Wide Web did not exist in the 80s. It really came around in the mid-90s. So remoting in would mean that you would have to have your machine ready and willing to accept calls. Yes, phone calls. Your machine would have to have a modem, a physical device back then, and you had to have a phone line on that modem, and you had to have your machine ready to respond or answer a call. You had to do too many things to get it ready. You couldn't just call a machine and get in and remotely and then begin accessing it. Today we have a lot of security issues. Do you have a camera on your phone? Do you have a camera right on your desktop or laptop? You know, there have been problems associated with that camera that is on your laptop or desktop. Some people have been known to remote into systems unauthorized and start looking at or viewing what other people are doing through their cameras. As a matter of fact, the new desktops and laptops come with a little feature that allows you to physically close. It's a little sliding bar thing that allows you to close so that your camera cannot be seen. Even if it's on, people can't see you because the lens is closed off, just like you would in a physical camera. So mobility issues and security issues really didn't exist with IPv4. This is something that needed to be corrected, fixed, enhanced in IPv6. So the obvious advantages of IPv6 over IPv4, no kidding, we have a much larger address space, much larger address space. The header format is much better. We have some new options, especially for mobility, for security, among other things. There is an allowance for extension. The way it's been written and handled and designed, it promotes the ability to extend IPv6 into the next generation, if you will. And there's support for resource allocation, substantially more secure, and great support for mobile devices. So header from IPv4 to IPv6. So here we have a 20 octet header, as you can see. And you have bits 0, as you can see, from IPv4 to 31. This makes it a 32-bit address. And then this is what we looked at already. So in IPv6, first of all, this is removed. This, let me erase all of my highlighter things. Okay. So the IHL type of service identification flags, fragment offset checksum, and option and padding are removed. Okay. And what's changed is this TTL, protocol, total length, source and destination addresses. Okay? All of this has changed from IPv4 to IPv6. So here's the header format. Take a look. So you got 10, right? And then you have 20, you have 30, right? There's 31. And you have your destination and source address, the payload, the next header, and the hop limit, right? Here's the IPv6 PDU structure. Okay, you have a mandatory IPv6 header right here. Right? You have a hop-by-hop options header, routing header, a fragment header, the destination options header, a TCP header, and then you have application data. This is the IPv6 packet body. All right? So something to keep in mind in the way this thing has progressed. There's a lot more of IPv6 to follow. IPv6 is very, very integral part of where things are going, and it's been in use and actively available for quite some time now.